JP4, JP5, JP8, Jet A, and so forth. And these are simply blends. So we have Air Force fuels for some of those. So we have a few Air Force folks. Which one do you usually use? You know? No. Yeah. Fly the aircraft. Do the fun stuff. Okay. So generally, it depends on what aircraft and what does the engine need to have. So for fighter jets, it's essentially Jet A, which is this is the Navy version, JP8. Between JP8 and JP3, that's the Army version. And think of it as diesel. These are very, very heavy fuels. Now, on the Air Force side, they're after performance, so it's Jet A is in between JP5 and JP8, but sometimes they run JP8. JP8 is a little bit more expensive because, again, think of it as your 90-something% at the pump that you're trying to put in. When you put the 90, well, or the $1.60-something right now, was it the 160s? Yeah, it's crazy, these prices. I gotta get a question.
How much does the fuel economy of the aircraft vary with the different types of fuels?
So very good. I mean, this is a research question. Essentially, and this is what we're looking at, is trying to optimize performance. It depends on the mission of the aircraft, like we talked before. Each propulsion system, you have to decide what is the mission. And in terms of fuel economy, in some aircrafts, it's not important. You'll say, no, I want the maximum performance possible because, well, I need to have high maneuverability, higher thrust, and so forth. But there is interest in doing long range as well. And that's where we're talking about hybrid cycles. And we'll talk about it further as we go into the semester. And this one I mentioned at the beginning of the course. I said, your generation is going to go out and do variable cycle systems, like the SR-71, the Blackbird. That was a variable cycle system. You're going to do that quite extensively to optimize when you have performance versus when you want fuel efficiency. So which fuels in general? Well, you can't say. Each one has a heat input in the end. Each one is going to give you the maximum Q, which we're going to get to in shortly. The heating value that's being generated, that's the one that you're interested in. So it doesn't matter if I use JP8, JP5, or JP8. It's how I'm actually burning inside that combustion chamber. So for this, it's a heavier fuel. Think of it as your 80-something grain that you're buying from a gas station versus your 90-something. If you put this versus this in your car, does it improve your miles per gallon? It might improve it slightly, but what do you get the difference between them? Cleaner, but what do you feel in your car? Why do race car drivers do 100% octane? What?
More
Sorry again.
horsepower.
What?
More horsepower.
More horsepower. So what does that mean? Performance. They're after performance. But if I blend it with other stuff, it's essentially, think of that when we talked about the rocks on the boat. What am I doing? I need to throw away mass to produce propulsion. So I can add some additives. I'm not going to burn essentially my combustor very efficiently, but I have some mass that somehow burns and gives me some thrust, but not very clean thrust, I guess. That's the way to put it. So in terms of fuel economy, and that's what we're doing for the Air Force, we're looking at blends with these fuels, with bio-based fuels, 50% blends. And if we do the lab tour, you'll come get to smell jet fuel in the lab. All right, any questions thus far? Okay, so moving on. So I have a fuel, and I have an oxidizer of some sort, and I need to burn. So I need to be able to characterize how much moles or mass of fuel relative to moles of mass of air in order to know what I'm putting into my system, which is essentially, we have to define our stoichiometric combustion. How many of you are familiar with the equivalence ratio? Can you raise your hand, please? The equivalence ratio.
Oh, equivalence ratio. That is equal.
Anybody familiar with stoichiometric conditions?
Are you talking like the ratio?
Okay, so let's revisit it. The stoichiometric ratio is ideal fuel to air ratio, and we're going to compute it actually. But, so this is essentially the main thing in propulsion systems, because you need to know how much fuel and air that you're mixing in order to be able to know how much energy you're really going to get. So stoichiometric combustion, what is stoichiometric combustion? So it's perfect match of fuel and oxidizer. No excess fuel or oxidizer. You need to be at that perfect mixture. If you're at that perfect mixture, then you're at that stoichiometric condition, meaning you cannot burn any better than this. This is the ideal burning condition. That's the maximum Q that you're going to get. So, ideal products that are generated. And I'll talk about it shortly. Which is essentially H2O and CO2. If you're using hydrocarbon, these are the two products. If I'm using hydrogen, all I'm going to get is H2O. So, if I take my fuel and air and I burn them at stoichiometric condition, what I should get is H2O and CO2. So, stoichiometric combustion, we're going to neglect any dissociation. Of products. Essentially caused by high temperature. You might get dissociation, things don't burn the same way you want it to burn because, well, your system is not optimized in terms of your combustor and you're getting heat losses or heat addition that you don't really need. So, example, what is an example of the dissociation? If I have water, for example, and have really high temperature, I can actually end up breaking up water in an undesired fashion. And what do I get? I'm going to get one molecule of hydrogen plus OH. So it's not an ideal situation, but it depends on the temperature level that you're working in. So I'm decomposing some of the compositions that I have. Now, one assumption we're going to make throughout this course is air is composed of, now this is very important, and write it down on your cheat sheet because you're going to need it when you're doing the midterm. Air is essentially 0.79 nitrogen and 0.21 oxygen. So, what does it represent? Essentially, 79% of air is really nitrogen and 21% is oxygen. Now, if you take air and you really analyze it, what you're going to end up with, this is 7, 8 something, and this is 20 and a fraction. And you end up with a smaller fraction of argon and all these different gases involved. But they're less than 1%, so we just ignore them. But throughout the course, 79 and 21. And this is based on the number of kilomoles. So let's try to do an example problem of determining the stoichiometric condition. So I'm just going to keep this up and start an example problem. Example. It's based on the same information that we already know of your molar mass and your mass fractions as well. So consider, let's say methane, CH4, reaction in air. Determine the stoichiometric coefficients. Okay, so methane, CH4, plus some air level. How much air should I decide? Right? So I need to decide how much air do I need to put in with my methane. And I don't know. I have primarily a amount of methane that I'm going to use, and I need to know how much air relative to that I need to put. So I'm just going to say I have coefficient A. So this is a coefficient. Some constant multiplied by air. And the composition of air, like I just mentioned, is what?
7921.
79%? So 0.79 of nitrogen plus 0.21